Thank you. Good morning, all. My name is Ashley. I work as a data scientist at CN, and my colleague Axel is also with us. Is so excited to be here at TMLS presenting our work, also learns from other industrial leaders. So today I'll be talking about our automated inspection program at CN. Let's get started. CN is a class 1 freight railroad and its network spans across US and Canada. So CN is responsible for moving commodities and goods, and many business depends on CN for moving the industrial products and intermodal shipping. So AIP, or Automated Inspection Portal, is an internally developed solution by CN for automatically identifying the defects on trains. So the trains pass through the portal at a speed, and there are high resolution cameras that captures 360-degree view of the train, and we have that's combined with computer vision and AI for identifying all the defects. Let's play a video. Can you please play the video?
Today, there are a lot of manual procedures in the railcar inspection process. People looking at railcars as they go by or as they stand in a yard, trying to identify the potential for defect. That process has worked for years and has helped CN maintain a safe and reliable railway.
Well, our daily tasks can be pretty challenging at times. When we do the certified car inspection, you're down on the ground, you're in the dirt, you're in the mud, you're in the trenches, you're doing a hard task. It can take up to an hour and a half, to possibly even 2. So what's very interesting about this is that we can take that time and reduce it down from an hour and a half to 2, down to minutes to seconds with a technology that is the automated railcar inspection portal.
So we're attempting to go from a completely manual inspection, where we use a human eye, to move toward a automated inspection through a portal, which automatically bad orders cars, and we get to do the repairs. These are high-resolution cameras pointed at the train, with the train going through at track speed up to 60 miles per hour. These are very large pieces of infrastructure with very high-intensity LED lighting that lights up the sides and the undercarriage of the train. With cameras all the way around taking pictures of everything, from what's underneath to the sides to the top, we get a picture of the entire train. A picture of every single car following the locomotive is captured 360 degrees. No matter what time of the day or night, time of year, there's no discrimination between the bad ordering of the car. So where a human eye may miss, the machine will.
It'll capture an accident before an accident happens.
Okay, as you see here, the main aim of the AIP project is we want to automate the certified car inspection using AIP as a mean of remote electronic inspection. So the remote electronic inspection could be a digital inspection by humans, or it could be an automated solution by AI models. So one of the key features, the benefits that we get from the AIP is it improves the operational efficiency with minimal inspection delays. So it provides that help us to get the network fastest operation, and at the same time we are able to detect all the defects in a better inspection quality. So this is how an AIP portal looks like. So there are 4 inspection portals that deployed with first generation of cameras that captures the side, top and undercarriage view of the camera. And additionally, 3 more portals with Gen 1 and Gen 2 cameras that captures the oblique view of, or angle view of the cars. So all these portals are equipped with line scan and area scan cameras, which captures approximately 800 images per car, So all these images will be sent to the inference engine for the defect detections. So these portals are located a little far away from the yard. So this inference engine will process these images and identify all the defects, and it generates the report, and this report will send it to the yard before the train arrives. So that's the way we save a lot of time. So before I go over my presentation, I would like to explain what is meant by the word use case. So because you would be hearing this word very frequently in my talk. So use case is that regulatory certified car inspection can be decomposed into multiple use case. So each use case focus on inspection of one or more rail components. For example, like identifying all the defects of, finding all the defective brake beams, or finding all defective operating lever. So that could be another use case. So it's just a machine learning pipeline for executing particular inspection tasks. So as you see here, you can see the, here you can see that workflow diagram. So that use case design flow contain many computer vision algorithms and one or more AI models. So for today's talk, I would be taking the use case called brake system types, that is for identifying the type of brake system. And I will be explaining what is the use case development process and what are the challenges we face. So before that, quickly I will just go through the life cycle of use case development and retraining process. So first it starts with the scope of use case. The subject matter expert, SMEs, they are very familiar with all the components, railcar components. So they provide all the details like how the component looks like or where it could be located in the car, how do they do inspection. So based on that, we get the use case requirement and we design a machine learning design flow. So in the design flow, we would be deciding like which camera we need to use. That's because we always need to get the best view of the component. Then we decide like in the pipeline, what are the computer vision algorithms need to be applied, what are the different AI models to be included. So based on that, we come up with a labeling strategy and label the data, or we collect the images from these portals and send it for labeling. Once the data is ready, we go for model training and choose the best performing model. Then we have pipeline testing, because in the pipeline we have multiple models, so we need to test the performance of every model in the pipeline. So at the end, we need to find whether that particular component is defective. So in that, we have a step called aggregations. We collect results of all the models and aggregate the results and come to a conclusion that whether that particular component is defective or not. So once the use case meet the targeted performance, we deploy it in the production, and after that we keep monitoring the performance. And if there is a team, they validate this use case result and they will report it as whether it's a valid or invalid result. So we collect all the failed samples and then it's go through the retraining process. So it's it's an iterative process. We keep improving the models till we achieve the targeted performance. So I will go in detail about this use case brake system type. So the main objective of this use case is identify the type of brake system. So in the bottom, you can see the image of a single car. It's a side view. And on top of that, it's the undercarriage view of the same car. So the brake system comes between two axles. So every car has two brake systems. So in the top, you can just see that highlighted one. It's the crop of that brake system that we call axle box. So inside the axle box, there are many components. So those are the components we need to inspect, like is there any defects or not. So if you see that image, there are two brake beams that is in the triangular shape, and inside the brake beam, you can see some brake lever. It has many pins. So sometimes we need to find, is there any pins are missing or not. So there are like different problems or different type of defects we need to be inspected on this ROI. So if I come back to our brake use case called brake system type, there are 11 different type of brake system. But if you look at these pictures, most of the types have very similar shapes and features. So if I take the brake type TMB, there is a cylinder on the right side of the triangle. If you look at the WAPCO, there are 2 cylinders. There are some components are different, so that those differentiating things that I highlighted with the bounding boxes. So the model should able to capture or learn these fine grained details, and it should able to classify this brake system. So many times we would have seen that the model has some class type, it's very difficult to classify, like it end up in misclassification. So we need to apply different strategies for the model to learn this and perform it well. So the first step in the use case is we need to generate the data set. So in the pipeline we have multiple models, so we need to generate separate data set for each model. So as you see here, the input image is the image of the single car. So usually it's a long image. This image is captured by a line scan cameras. So usually the image resolution would be like 1024 by the width would be like 5000 to 10,000 pixels. So the technique that we use the sliding windows, generate the slices, then go for the detection. So in the pipeline, the first model is detect axle box. So these slices are sent to a detection model and locate the axle box. And after that, we have 2 more models to detect the brake beam, that is the triangular region, and another one is a classification model. So we generate this data set and send it for model training. For model training, we use state-of-the-art convolution neural networks like segmentation, detection, and classifications. And at this point, we apply different augmentation techniques and hyperparameter tuning. So we have a training tool that perform the hyperparameter search and choose the best network. So the best performing model will be send it for the testing. So another important step in the process is the pipeline testing. Because as I mentioned, in the pipeline we have multiple models. So as you see here, like in the pipeline we have 3 models. The performance of the classifier can be impacted by the performance of the upstream model, like here the detection of axle box. For example, if you miss the bounding box prediction, or it's a shifted bounding box from the upstream model, that would affect the performance of the downstream model. So we need to make sure that the model is robust enough to handle this kind of thing. So we have a technique to regenerate a random shift data, and we train the model to make sure that it's able to perform well even though the data coming from the upstream is shifted. So in the pipeline testing, we generate different metrics like precision, recall, F-score, and we validate the performance. The performance of the model at pipeline is very similar to what we see in the deployment. So it's always we need to make sure that we get the right metric here. Once we get the good metric, then we do the aggregation. So here one example for an aggregation rate is like every car we expect a 2 brake system, and every brake system will have 2 brake beams. So one aggregation logic would be, we would be checking whether there are 2 brake beams are present in a single axle box. If one is not there, it could be a missing brake beam. So after that, once you aggregate these results, we apply different business logic. Suppose if you want to say whether a brake beam is defective, for a mechanic they have different rules, like suppose they expect 3 pins in a brake lever. So suppose we can go for a count and see whether that many pins are present or not. If it's not there, it could be a defect. So this is a very simple business logic. Sometimes we have to go for a measurement, how much angle that component is located. Like there are a lot of complicated logics also. So based on that, we come to a conclusion that the particular component is defective or not. So this brake system type, this information we use for developing other downstream use cases. One of the use cases is finding a missing brake beam. So missing a brake beam, as you see in the left image, the left hand side, the triangle beam is missing, and the right side you have the triangle beam. So it's a like slightly easy ML problem. You can have a detection model, just try to find the triangle. If the triangle is not there, it's a missing beam. But collecting images of the missing beam is a very challenging problem. So every day through the portals, hundreds of trains are passing and thousands of brake beams images are getting. But finding a car with a missing brake beam is a very rare defect. So at the end, like the number of images we get for missing brake beams would be very less. So at the end, we will have a very imbalanced data set. Even not only this defect type, so even if you see the diagram, that is a data distribution for the brake type. So some type of brake type would be very common compared to the other one. So if you see that one of the class has like very high distribution compared to the other class. So most of the data set we will have these kind of imbalanced data set. So so train a model with this kind of data set is always a challenge. So we explore different strategies to get a best performing model. So one of the way of handling this is we oversample the defective classes. So we generate a synthetic data and increase the number of samples for that particular class. We apply different augmentation technique and enhance the data set. Even in railroad data, all the general augmentations may not be applicable, so we need to carefully choose what kind of augmentations are applicable. And many times we have a lot of images that covered with snow, so we use snow augmentations to generate a samples for that. Another thing, like we have a lot of railcar data, those are unlabeled. So we thought we can use a self-supervised model learning and get a model that the model is very specific to railcar domain. So we trained as SSL model that we used as a pre-trained model for transfer learning and fine-tuning. Also, this SSL model can be used for selecting the unique samples. So another approach is like we have non-defective classes, the number of samples available are very high. So what we can do is we just downsample that particular classes. So we use a SSL model, extract the image embeddings, then we compute the unique samples. So that makes sure that we get all variations of the components included in the data set. Especially in the railcar, like we see a lot of components, there would be a lot of variations. Like even if we take a brake beam, there would be like many variations would be there in the data sets. So we would, so these steps help us to find all kind of data distribution included in the training data set. Then another way of handling this one is that we have used weighted class loss. So the weights can be tuned based on the number of classes, number of samples per class, or we can use it as a hyperparameter in the tool that will find the best weight for getting the minimum loss. Then another use case that use the brake type is the defective brake beam. Like this brake beam can be broken or it's a bend. So here the main challenge is it involves a lot of subjectivity. For example, here the brake beam can be slightly bent, may not be considered as a defect. The labeling is very challenging. So we always need an expert input which they consider as a defective or non-defective. So whenever there is a subjectivity involved, the model gets so confused whether it goes as a defective or non-defective. So many times we have to revisit the labels again and keep fine tuning. Like most of the time we observe that we end up in many iterations to get the best performing model. Another way we could solve this, if we could have a mechanism to measure the severity of the defect, especially here, if we can measure that, okay, how much degree or in some quantitative way we can measure the defect. But we felt that it's a very difficult problem. Like here, we don't have a method right now to measure how much degree the beam is bent. Still, it's an open problem. This is another use case that we use missing brake pins. The main challenge here is the pins are very small. So if you see the pins, the down, I have the diagram, it will have a head and 2 legs. But the number of pixels for that representing that pin is very less. So for this kind of scenario, what we do is we define a region of interest that like we have an idea like where these pins are expected to be. So we define an ROI in such a way that there are other pins or other things that comes in the background will get excluded. So that is the way we could reduce false positive. Another way, right, like so we have a segmentation model to segment the liver. So we know that pins are going to be in the liver. So we can exclude the other bounding boxes get detected in the this ROI. So here again we use other techniques like image padding to make upsample the image before it's sent to the trainer. Then we use different image enhancement technique because if the image is not bright enough, the model won't be able to detect these pins. Then different hyperparameter tunings are tried. Another challenge that we face is like image quality. So these are some of the images that we collected from the portals. So the first image, there are streaks at the center of the image and it masks most of the components that comes in the center of the image. And the second one also has some streak, but it's not significant as the first one. And the third image is a dark image. The fourth one has like more exposure and it's more brighter. But even though the fourth one is brighter, but still you can see the axle box and its components clearly. So in this kind of scenario, we don't want to remove that image still because we can still see the components. So we want to measure the image quality at different level. So for that, actually we have like a dedicated machine learning pipeline to monitor the quality of the image. So like first we do image quality analysis at image level on the whole image, like especially image brightness, how dark the image, the blurredness of the image and the streak. For streak detection, we have a classification model, so that will identify like high, severe, low images. So we flag and filter all low quality images to prevent inference for the downstream use cases. So only the good images are sent it for the inference. And one more step we added, that is the component level analysis. So once it passed the image level analysis, we go for a component level image analysis. The reason is that like based on different use cases, our criteria for the image quality filtering is different. For example, if I go back to this slide, the first image, it looks good. If you look at the third image, it masks some of the components at the center. But still this image we can use it for detecting a triangle beam, because still we can see the triangle beam and the features are good enough. So based on the use case, we generate different rules or a different threshold, and based on that we will just filter out the images. So for, again, if I take the third image, we cannot use that for a pin detection, but we can use for a missing brake beam use cases. So same way we set different threshold for every use cases. That is the purpose of component level or ROE level analysis. In CN actually we use computer vision and machine learning for automated inspection of rail cars. So we leverage the right data and computer vision approaches. So we are able to get effective solution for inspecting the cars. So we have around 70 use cases already deployed in the production and more to be developed. So these use cases are constantly being improved through retraining. So there are many use cases still in the production. So and around more than 300 models are already deployed. Advances by AIP at CN are like driving high operational efficiency while ensuring fluid network. Hope you got some idea like what CN is doing on automated inspection space. So I'll be here today and tomorrow. If you have any questions regarding my presentation, or if you would like to CN, please reach out to me. Thank you.
So we might have time for one or two questions if there are any. There's a mic over there, so if you want to go stand up there and ask the question, that would be great.
Thank you for the presentation. Very interesting use case for computer vision. So my question is, what's your success rate / accuracy right now, and what's the number that you're looking for? Because at the end of the day, are we going to replace the human inspection, or is going to be a decision support system? And what's the gap that we are now trying to fill in? Thank you.
Can you repeat the last part of the question?
So from the regulation perspective, I'm not completely familiar with the codes on the railway, but for example, if a human inspects one of the cars, what's the tolerance for error that you could expect? And now your model, what your success rate? Because at the end of the day, and this is also important, that are you going to replace the humans in the loop, or is you going to operate as a decision support system?
Yeah. So the images that we upload to the inference engine, we get the inference. These results will be analyzed by humans, as well as we get the reports by the AI models. So when the humans are in the loop, they do the inspection and they see the performance of the model. And if the model is always correct, then we know that our model is performing well. Then we can automate that use cases. So if you take our 70 use cases, some of the use cases are completely automated because that AI predictions are always correct. But some use cases still there is need to be improvement. In those kind of use cases, there would be a human in the loop, and they will make sure that we don't miss any defects, because these are very safety critical applications.
Thank you for the talk. I have a very short question. Could you elaborate a little bit more on the snow augmentation to the images?
Yeah. So especially during the winter, a lot of snow get accumulated on the rail cars, and in the image you will see a lot of snow. So again, what kind of data you use for the training? Suddenly you just give an image with the snow, the model will fail. So what we do is during the training, we try to include images with the snow. Always, other than that, we add snow augmentation that in the image. So we add that particular augmentations to make sure that the model is robust enough to handle the snow images.
Thank you.
Hi, thank you. Good talk. I work in auto, so I'm very well aware of some of this operational complexity and there's many ways that something can go wrong that's related to something down the chain. I'm curious to integration to any kind of other like multimodal vision systems. So I read some papers on some folks using stuff looking at thermal sensing as well. I guess one issue that could arise is you gave an example of the pins that we had like at work for us too, was the pins may look okay in the image, but sometimes they may be, their temperature may be more than we needed to be, right? And that could cause issues down the line in terms of wear and the amount of time that, and the amount of time that they should be operational. I'm curious, have you found limitations with only using vision?
Okay, so whatever today's talk I was covering only like we use RGB images, and right now we don't use any thermal sensor because the components can be heat, like we don't use the thermal images. But we are planning to have a depth sensors because sometimes, suppose if you want to find a missing pin, there would be a hole. But if you take a RGB image, the hole or a black dot can be very difficult to differentiate. So we don't. So what we are thinking of like adding a depth sensor that give a more perspective of the severity of the defects. So right now we use only RGB images.
Okay, thank you.